So welcome back to the aerodynamics class. So today we will be discussing on the vortex sheet and then Kutta condition, and then we will have a look into the Kelvin's circulation theorem, right? So I acknowledge John D. Anderson's fundamentals of aerodynamics, right? Now let us start with the vortex sheet. We already know what the vortex is, right? Say, for example, if I say the vortex is about this point, then one can draw the vortex like this. Right? So we can say that the vortex, I say it is in the clockwise direction, and this is the point O, right? The origin, right? And this can be defined as a vortex, right? Now, I would like to have a vortex filament. Okay. Now, assume that this particular screen, from the screen in and out, I take this particular line, right? So, please imagine. So, this particular line, right? So, this particular line now have another vortex here. Right? And I mark the direction also. And anyone can take a particular point and can see the vortices, right? From the origin O, right? Say from the screen and on the from beyond the screen and perpendicular to the screen, I take this as minus infinity and this is plus infinity. So this is the filament, right? So this is actually the vortex filament. Let us say vortex filament. And now individually the vortex has a strength, and there is a vortex strength, right? So the total strength, if I say the strength is gamma. So this filament, the straight vortex filament of strength gamma is the point, right? So vortex filament of strength gamma, right? I can write. Okay, so this is the vortex filament. Okay. Now, okay, so I have shown only the two vortices in the filament for a representation, but it is not necessary that there is only two vortex, the source, but also can have multiple number of vortex source, right? And this gamma is the integrated strength of all the small vortices, right? Now we have another discussion. Say I will take this coordinate system as X and this as Z, and here it is Y. I recommend you to take down, right? Now we have initially we had a point source of vortex. Now with the filament I can say that this is a line source, right? Now if I keep the line source, say let us say I have a filament and another filament and another filament, another filament. Right? So the every filament we will have a filament strength gamma, right? So as we had discussed, here it is minus infinity and here it is plus infinity. Okay. Right. So infinite number of line sources arranged in a side by side with the strength of each line source, which is being infinitely small, is considered. Right. So this is called vortex sheet. This is called vortex sheet, right? Now, say if somebody look from this side view, I mean the edge view, and if they draw, then it will be, we can see that, say in the XZ, right? So if it is a XZ, then we can draw something like this, and you will be seeing the, sorry, right, along the line, and each and every point is a filament. So I say that this is point A and this is point B, and the length of the filament is, say, S. If I say yes, then the elemental length is ds, right? Now, I take a particular point, say any point on the sheet, and I would like to say the effect of that particular vortex sheet on the point P, right? So the point P is located at a distance R, right? Say it is located at a point R, right? So let us say from ds. Okay, ds can be any elemental. So this P is x comma z, right? Now the small section ds, right? The small section ds of the vortex sheet have a strength of gamma, right? So we can say that the vortex strength gamma into ds, right? So this gamma into ds induces an infinitesimally small velocity dv, infinitesimally small velocity dv at point P. Please note it. You have a ds is a elemental length, right? And we have a vortex sheet of strength gamma, right? This vortex sheet of strength gamma, which I mentioned, is for this particular elemental length, right? So from this, one can write the induced velocity dv is equal to, I hope you remember the v is equal to gamma by 2 pi r, we have derived some times back, right? So dv can be written as, it was minus. So this can be written as minus gamma ds by 2 pi r, right? Now it is very much convenient to represent anything in terms of velocity potential. So let us say the increment in velocity potential, say increment in velocity potential is d phi, right? So this d phi is a velocity potential induced at point P by the elemental vortex gamma ds. So we already know we can write d phi is equal to minus gamma ds by 2 pi into theta, right? So if one want to have it for the entire vortex sheet, then we can have phi of x comma z is equal to minus 1 by 2 pi integral a to b gamma theta into ds, right? So this velocity potential will be very much useful for our further discussion in thin airfoil theory, right? So please note how we are arriving to this particular point, right? Now the circulation, we already know the circulation, say gamma is the circulation around a point vortex is equal to the strength of the vortices, right? So the circulation around the vortex sheet is the sum of the strength of all the elementary vortices. So in this case, I can write A to B gamma ds. You remember the gamma in this each and every elemental vortices and the ds, and we can write this as. Now consider, say we have a, let us say, I will write here, we have a vortex filament. Say at every point you have a vortices, right? Now I take an rectangular dashed path to just represent in order to calculate the circulation, right? So I will take this as say dn, and this is ds. Okay, and I can say that this velocity u1 and this velocity u2 and this velocity v2 and this velocity v1, right? So the velocity components tangential to top and bottom of the rectangular path is u1 and u2, and in tangential left and right are v1 and v2, and they are separated by a distance, say dn and ds. So this is actually the tangential velocity jump across the vortex sheet. So now, okay, this is minus probably. So the circulation around the dashed path, right? So let us write the circulation around the dashed path. We have already done some exercise like this, right? So let us write gamma, right? So we can write gamma is equal to minus, I start from V2, so V2 into dn, right? This is V2 into dn minus u1 into ds minus v1 into dn plus u2 into ds, right? So this can be written as u1 minus u2 into ds plus v1 minus v2 into dn, right? So here the strength of the vortex sheet contained inside the dashed path is gamma into ds, right? So say when we will have a limitation that when dn tends to 0, right? That means that the top and the bottom approaches, right? Then we can write that gamma into ds is equal to u1 minus u2 into ds. So the circulation gamma can be written as u1 minus u2, right? This is actually the local jump in tangential velocity across the vortex sheet, which is equal to the local sheet strength, right? So please note it. So this is for a vortex sheet I have taken. Now the real problem comes now. Let us consider an arbitrary shape. Maybe let us consider an airfoil with an arbitrary shape and having a thickness, right? And it is subjected to a free stream velocity v infinity. Okay. And one can define the gamma in that case is also integral gamma into ds. So let us assume that airfoil. this is an airfoil having a thickness, and here you have a V infinity is a free stream velocity, right? Now I consider the sheet of vortex. Right? So I can say that this is gamma of S, right? So if one want to calculate the um, circulation, and finally if one want to calculate the lift force L dash, that is lift per unit span as per the Kutta-Jaworski theorem, we can arrive at L dash is equal to rho infinity V infinity gamma, and this gamma is the integration of the whole over a whole S length and gamma into ds. So this is how we will arrive. Okay. Anyway, all these information will be very much useful for the thin airfoil theory. Thin airfoil theory. That we will discuss in the next class. Right. So please remember, we start with the vortex filament, and then we had a vortex sheet. Then we have derived the incremental velocity and incremental velocity potential. Then we have considered a dashed path, and then for that we have calculated the gamma, and then we had a thinking that how we can apply this to the whole airfoil, and we have arrived to this part. Right? Now, the second topic, today's second topic is Kutta condition. In the last class, we had a discussion. The discussion is about the Kutta-Jaworski theorem, that is L dash is equal to rho infinity V infinity gamma. And now we will have a Kutta condition. Right? So, for any given airfoil, right? Say for any given airfoil, I would like to say the airfoil, any given airfoil. Okay. If you have an airfoil, you have two possibilities. One possibility is this trailing edge, right? This trailing edge can be of I take only the trailing edge, right? The trailing edge can be finite. Okay. So if the trailing edge is finite, then one can write like this. Say this is V2 and this is V1, and this is the point A. So at point A, this V1 is equal to V2. Now what happens if the trailing edge is cusped? This is another possibility. What happens if the trailing edge is cusped? So this is again a point A. So if this is cusped, then you will have a flow like this. Again in the bottom also you will have the flow like this. You will have a velocity V1 and velocity V2. So at this case, say at point A, V1 that is equal to V2 but not equal to 0. Okay, but in this case it is equal to 0. If it is equal to 0, then this is a stagnation point. Okay. So let us start the Kutta's condition. Kutta condition. The first condition, for a given airfoil, right? For a given airfoil at given angle of attack, the value of gamma around the airfoil is in such a way that it leaves the trailing edge smoothly. Leaves the trailing edge smoothly. For a given airfoil at a given angle of attack, the value of gamma around the airfoil is in such a way that the flow leaves the trailing edge smoothly. That is the first Kutta condition. Okay. Now, second condition. If the trailing edge is finite, if the trailing edge is finite, what is finite? This is finite. If the trailing edge is finite, then V1 is equal to V2 is equal to 0, and then it is the trailing edge is a stagnation point. Okay, third condition, what happens if it is cusp? If the trailing edge is cusp, the trailing edge is cusp, then the velocities leaving the top and the bottom, right, are finite and equal in magnitude and direction. That is, V1 is equal to V2, which is not equal to 0. Right? So, right? So, as we know already, gamma is equal to U1 minus U2. Gamma is equal to U1 minus U2. And hence, we can write the strength of the vortices, that is gamma, at the trailing edge. That means at the point A is equal to V1 minus V2. So what happens if the Kutta condition 2 case, that is at finite trailing edge, the gamma at the trailing edge is equal to 0, right? In the third case, it is not equal to 0. Here it is equal to 0. Now, at the third point, if it is cusp at cusp trailing edge, then V1 is equal to V2, but not equal to 0. However, your V1 minus V2 becomes 0. So therefore, the Kutta condition expressed in terms of strength of the vortex sheet as the gamma is a circulation in the trailing edge is equal to 0. Right? So anyone should say the Kutta condition, right? the strength of for a given airfoil at a given angle of attack, the value of circulation around the airfoil is in such a way that the flow leaves the trailing edge smoothly. Second point, if the trailing edge is finite, then the trailing edge is the stagnation point. Third one, if the trailing edge is cusp, that is V1 is equal to V2, but not equal to 0. So we already know the gamma is equal to U1 minus U2, that we have arrived before in the vortex sheet discussion. So we can say that at a finite trailing edge, the gamma at trailing edge equal to 0, at a cusp trailing edge, gamma trailing edge equal to 0. Right? So this is the famous Kutta condition. So any aerodynamist should know about it. Right? Now we will go to the Kelvin's circulation theorem. Okay. So I will just draw, say there is a fluid flow. Okay. Now there is a curve C. Okay. I would like to have a curve C. Say the fluid elements along the curve C. So let me draw in this way. Right. So let me say the curve C1 having a circulation gamma. Now there is another curve. Okay. Right. Another curve, say the curve C2 and having gamma 2. The same fluid elements. So this is at time T1 and the same fluid element at later time T2. Right. Now the fluid elements form a different curve C2. Right. The same fluid element here and here also the same fluid element, but it forms a curve C1 and the circulation gamma 1 here, and here it forms another curve with the circulation gamma 2, right? Both are two different curves. So let us consider an arbitrary inviscid incompressible flow and assume that the body force is 0. Then we can write gamma 1 is equal to minus integral, say curve C1 V into ds. Similarly, gamma 2 is equal to minus integral V into ds, but this is curve C2. Now we can write gamma 1 is equal to gamma 2. That is the point here, right? We will come across. And the substantial derivative, if one want to consider d gamma by dt is equal to 0. So the mathematical statement of Kelvin circulation theorem says that the time rate of change of circulation around a closed curve consisting of the same element is 0. Right? So let me write that the mathematical statement says that the time rate of of change of circulation around a closed curve, consisting of the same fluid element of the same fluid element elements is 0. So this is the Kelvin's circulation law, right? Kelvin's circulation theorem. So please note it, and it will be very much useful when we do some starting vortices that we will have a discussion now, right? So let us consider an airfoil, right? So we will have an airfoil. Okay. So here you have a velocity v infinity. Say now the v infinity is equal to 0. So I consider a closed curve C1. This is a closed curve C1. And now the velocity is 0. And in the airfoil, right, this is the airfoil. And in the airfoil, so around, if you say the circulation is 0, that means the fluid is rest relative to the airfoil. Okay. This is case A. Now you have a finite velocity v infinity. So when you have a finite velocity v infinity, this is the airfoil, is at some angle of attack, right? So it will have a, say, it will be having an starting vortices, right? Say for example, at the first moment, so when the flow is started, a thin region of very large velocity gradient is formed at the trailing edge, right? So this vorticity region, say it will be like this, right? Right. So this, what happens is this formed and it got flushed, and over a period of time, in the downstream, you can see this particular vortex. So as it moves to the downstream, this thin sheet of intense vorticity becomes unstable, and it tends to roll up and form a picture, right, which is similar to a point vortex. This vortex is called starting vortex. Okay, this is what happening when you have a finite velocity v infinity. Now let me draw a curve. So let me say this is the curve C2, And what I will do is like I divide this into two. Right, I want to have one airfoil and another one is the starting vortex. So let me say a point A here, and here it is a point B, and here the point C here, and the point D here. So A, B, C, D forms a closed curve C2. Right. Now, because of the starting vortex here, it will be having an circulation gamma. Say I will call this as gamma 3. Right. Whenever you have a gamma 3, this is not. So if say if C2 at C2 or beyond C2, if it needs to maintain that it is 0 or there is no effect of this airfoil, this gamma 3 should produce another gamma, say gamma 4. Right? When it creates gamma 4, so one can say that this is gamma 1, and I say around the C2, the circulation is gamma 2. Gamma 2 is now become the summation of gamma 3 and gamma 4. Right? So please understand, first case, the airfoil is stationary and the velocity is 0, and hence around the closed curve C1, you will not feel any difference. The fluid is at rest when compared to the airfoil. Second case, right? We have a finite V infinity. This is the second case. The velocity V infinity is there, and in the airfoil, initially there will be a formation of the because of the pressure difference, there is a formation of vortices that gets flushed down, and when it gets flushed down at the downstream, it forms a intensive vortex of strength gamma. So this is called the starting vortex, right? So the starting vortex have a strength gamma 3, and this in turn produces some gamma 4. Say if we say only the gamma 3 exists, then there should be definitely a gamma 4 exists in order to have a gamma 2 is equal to 0. So we say gamma 3 and gamma 4 is equal to 0, then gamma 3 is equal to minus gamma 4, or in the vice versa, or in the reverse. So now you can imagine when there is a fluid flow, how one can calculate the lift L dash based on rho infinity, V infinity, and gamma. So the gamma is produced here, that in turn creates the lift force. That is the beauty of the theoretical aerodynamics, right? So I stop at this point, say in Kelvin's circulation theorem, and we will continue in thin airfoil theory in the next class. Thank you very much.